To understand how a machine discovers new materials, you have to start with the physical reality of a molecule. It exists in three-dimensional space, a continuous, vibrating structure bound by the laws of physics and interacting with countless environmental variables. But a computer cannot see, touch, or feel chemistry. It operates purely on electrical state changes, processing binary data in silicon chips. To evaluate this molecule, the system must force this physical object through a severe computational bottleneck, translating it into a format a machine can read. Because the algorithm cannot process the infinite complexity of physical chemistry directly, it requires a deliberate, destructive process of lossy translation to make algorithmic judgment possible. The first step discards the complex 3D physical shape entirely, collapsing the molecule into a single flat dimension. This format is the SMILES string, which represents the entire molecule strictly as a line of standard text characters. A string of letters captures the chemical ingredients, the specific atoms and their connections, but sacrifices the molecule's spatial geometry and orientation in space. The infinite, unmanageable nature of the physical object is now contained entirely inside a computable string of text. While text is computable, a raw string of letters is too abstract. A predictive model cannot easily analyze structural relationships from a sentence. It needs a spatial format. The system reads the letters and reconstructs the atomic connections, unfolding the flat text back into a skeletal, virtual structure. The computational engine performing this reconstruction is RDKit. It acts as a chemical translator, mapping out the specific atoms and the connective bonds between them in system memory. This resulting mathematical graph allows the computer to navigate the molecule's topology, bridging the gap between a flat line of text and a computable structure. Even as a graph, a sprawling molecular structure is still too fluid for a rigid predictive algorithm to evaluate as a single whole object. The Morgan fingerprint isolates specific, localized chemical neighborhoods. It begins by capturing a single target atom, a radius of 0. The scan expands to capture immediate neighboring atoms, then expands a second time to capture neighbors of neighbors, recording a distinct local pattern. This concentric rippling scan repeats systematically for every single atom across the entire molecule. This process deconstructs a fluid molecule into a measurable collection of overlapping, isolated local chemical patterns. But thousands of variable-sized local patterns take up too much unstructured memory and cannot be directly compared to one another. The system applies hashing, forcing every captured chemical pattern into a strict mathematical grid. Specific chemical patterns trigger specific bits to turn on, forming a long binary vector. The molecule and its graph now exists as a fixed, highly compressed binary memory, structural traits formatted for algorithmic judgment. This binary vector moves out of the formatting phase and directly into the system's predictive modeling core. The decision engine is a random forest, a machine learning model composed of thousands of individual rule-based decision trees. The binary vector is fed into these trees. Specific on bits force the data down distinct branching microscopic pathways. Each individual tree evaluates the same binary memory through a slightly different set of strict rules, providing a unique perspective. Utilizing thousands of rigid rules and isolated perspectives creates a robust evaluation system capable of judging abstract chemical memory. At the end of these paths, each tree casts a single vote. Those thousands of individual votes combine into a single calibrated probability score. Zooming out, we see the true scale. This translation pipeline processes thousands of unique molecules simultaneously in a continuous, high-speed flow. The system ranks the molecules based on their probability scores, prioritizing the most promising candidates for physical lac testing. The algorithm operates exclusively on derived binary patterns, isolated from the sensory reality of physical chemistry. While the system only operates on abstract mathematics, its predictive power depends on how those patterns were distilled from the raw geometry of the original molecule.